Hello, ladies and gentlemen. My name is Jan. I build stuff so you don't have to. So in the latest episodes we found out that conventional cooling via fans or even compressed air just doesn't cut it if you want to go sub, let's say, 3 minutes in terms of printing a Banshee. To reach our final goal of doing it in sub than 1 minute, we have to crank it up a few 100%. Let me show you. So let us have a look. This would be one of the first things I had in mind. Unfortunately, we're not going to do that for various reasons, but I think you get the idea as of a print bed. So imagine your Banshee right here. We have shop air coming from this side. So if you have a look on top, this is slightly offset to one side, and this will be a stream of air going this way across the Banshee, and vice versa. I've gone back and forth with this design, and it turns out to be too massive and too heavy for my application, and it also needs to have at least a 6mm diameter tube going in here, so we're not gonna do that. I don't think it makes any sense, but just as an idea out there, if anyone wants to test something like that. Okay, moving next in line, we got this freaking contraption here. And yeah, this is basically just a box filled with water, and submerged in there is some kind of a ultrasonic vapor device. If I turn on the air in the back, you'll see that it produces a nice, very fine water vapor. And if we're just using air, we are pretty much limited by the density and also the heat capacity. So water itself is 1,000 times more dense than air. And by just applying the right amount to our cooling stream of shop air again, we can up our cooling capabilities by a few 100%. So this is basically the route of changing up our media. We could totally do that by going with different gases. Helium, for example, would be a great example. It has 4.5 times the heat capacity as usual air. So that would make up for great cooling capacities, but helium is way too expensive for these tests to run. So this is about changing the cooling media itself. As many of you people pointed out in the comment section in the last video, we could also try to increase our temperature delta from the cooling media to whatever we're trying to cool. In terms of the PLA we're using, we're somewhere in the 200 degrees centigrade range. And the usual shop air will be, after expansion, somewhere in, like, let's say, room temperature. That makes up for a delta of 180 degrees C. So we could up our cooling game by also a few 100% if we get that gap a lot bigger from what we're trying to cool and what we're trying to cool it with. And we're going to do that by this little device. So this is basically a steel container of, let's say, 2 liters of volume, and then it's insulated with some styrofoam on the outside, and then we have a copper tube bent in here. And what this allows us to do is basically run the shop air before it exits the nozzle, and then ultimately at the print, we're going to run it through this cooler and see how big of a temperature difference we can make. So you're wondering, what kind of cooling media could we use to cool down this copper tube? Well, yeah, first of all, and this is, I guess, the first test we're going to conduct, will be done with dry ice. So basically this is frozen CO2, and it should be somewhere in the range of minus 78 degrees centigrade. We're going to see, and I've did some calculations on this, how much of that we can transfer into the cooling media and how much the cooling media will actually pick up from, let's say, the exit to the actual print, which will be right up around here. And then, if this is not enough, this is for the big boy. So this is liquid nitrogen, should be at around minus 180 degrees C. And we're basically going to do the same as with the dry ice. We're going to put it in this container, seal it up a bit more with insulation, and then see how much we can cool down the air exiting. And on the way, we're going to find out what this actually does to all of the rest of our hardware. And yeah, you may be wondering what might be the best scientific method of actually comparing all these different approaches. And yeah, for the very start, we're gonna do that with two things. This is a benchy I printed with the current setup. As you may see, we changed the filament color to black, and this has been running 3 minutes 20, I guess. So this is like a baseline for what is possible with the current setup. We're gonna do a benchy of the same sort with the different cooling medias and see how that compares. And on top of that, I've been designing these. And for what it's worth, I tried to come up with a benchmarking solutions to actually verify our data. These cylinders are printed at increasing feed rates. And this has a very special side effect because this is a known layer time. So this will start, and this is my scale to it, from 100 millimeters per second to 1500 millimeters a second. And this corresponds to 4-second layer time down here, all the way to 0.4 seconds of layer time up here. And I've been fooling around with these quite a bit, and I then settled on this guy here, which does have some infill and gives some more data points, I guess. Actually, while doing these, I discovered that you can derive so much from these prints, actually, in terms of pressure advance values, in terms of seam lines, in terms of surface artifacts, etc. But what goes through all of these test prints is that my sweet spot seems to be somewhere down from 1000 millimeters a second printing speed. I'm nowhere maxed out in terms of the hot end. I could go way above with a 0.4 millimeter nozzle that I'm using right now. I could go up to 3 meters per second just in terms of volumetric flow, but we discovered in the last episode that cooling is the issue. And this metric seems to be going through all of these prints somewhere in the 1 meter per second area. This is going bad. So, in this episode, we're trying to find out if we can use these benchmarking prints to actually set all these different approaches in context and see which one we're going to investigate further for our sub 1 minute quest. I hope you're hyped, just as I am. Let's roll the intro tape, and then I'm going to tell you something about today's episode's sponsor, as well as the new parts that actually went on the machine. Have fun.
Da 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 da.
So just like in the last episodes, this video has been sponsored by PCBWay. They do manufacturing of all sorts, like 3D printing and various processes, sheet metal, you name it basically. This is one of the latest parts that actually got on the machine, which is this stainless steel cover. It bolts up to the M3 screws here on the LGX Pros. And yeah, down here you can see it basically capsules this whole section here. So I was having that manufactured in preparation for everything we're gonna do here with the cooling situation, because I knew once I get with vapor in here, it will actually blow my hot and cool. And yeah, that would be kind of bad for the process. And if you have a closer look here, the thing down here right in the middle is actually an SLM printed stainless steel thing, which is just covering all of the nozzle itself. And again, this was a really easy setup. I just catted it up in Fusion as a pretty standard step file, sent it over, put it on their website. An engineer took a closer look at that part, and if you have any idea about sheet metal bending, this is actually not the easiest part to do. It has a lot of cuts in it, as well as how to do that geometry down here. It has a really nice surface finish, which I selected beforehand. This is a brushed 320 grit something. And yeah, it just fitted on here, which is remarkable for its being like somewhere in the neighborhood of 50 bucks. So yeah, again, the collaboration with PCBWay is what is enabling me to do all these crazy projects here. They have been delivering all the crazy parts that went on here in the most different processes. So there is a link somewhere down in the video description where you actually do get a discount on your first order. So check that out. And then let's have a look at the different things that went on the machine in the last couple of weeks. So as you can see, after we crashed the machine in late night testing, there is a new glass plate on here. And since this is a millimeter thicker than the previous one, I had to redo this part here. So essentially the aluminum plug that is in here is the same as before. This has been the earlier version and I wasn't too happy about it from the very beginning. As you can see, this is kind of rocking. And then this configuration of anchor points from those cables did give me a hard time programming the kinematics in the machine. So in this prototype, and you can't really see it here, but both of these cables connect to a single mating point, and that makes it way easier for me to set up the firmware. Then again, I took the chance and relapped it, this time in a different approach. I lapped this part until it was completely flat and parallel on both sides. Then I took a good measurement and then actually took 4 of these steel blocks and surface ground them to the exact fit I want to have. Right now this is at about 30 microns of clearance for the air bearing to ride in, and it works really well with comparably low amounts of pressure from below. Well, on the subject of what I did change from the last episode, so as you can see, we got a new mainboard actually, and the processor, the BigTreeTech Octopus Pro, was working like a charm from the very first minute on. I wanted to get rid of all that wiring with the accessory stepper drivers. This was kind of a mess and led to some unknown errors, etc. Because these offer insane values and opportunities to hook stuff up to. There are 4 drivers which are like somewhere in the neighborhood of 8 amps of current, something ridiculous like that, and the other 4 are like 3 or 4 amps, still pretty beefy. And this is a perfect setup for me because I can hook up all those drivers with a sophisticated big connector on there and proper wire sizing. And then of course it has all the goodies. So basically if you want to go for speed printing, this is the H723 SMT processor, which is basically the processor to go in terms of computing power. It has all the accessories you would see in a high-end board for a really affordable pricing. You will find a link somewhere down in the video description leading to that website. So yeah, I've been really happy with these products. And then, don't mind the mess here. I got a new power supply to get rid of the old bulky one. It was taking up a lot of space and I needed for another project. Also, this is capable of delivering 20 amps up to 60 volts. So that was something I was missing before. The old power supply was only up to 40 volts. Also, I put in some breakers to get very quick access to all the powers going in and out of the board. Okay, when comparing this stuff, let's check out what the previous solution was doing in terms of cooling capabilities. So this is a nichrome temperature probe, and what I'm going to do now is blow actually compressed air on the tip of it and you can see the readings. Headphone users beware. So essentially the lowest temperature I can get a reading of is somewhere in the range of 5 degrees or something, depending on where I point the thermistor in this case. I mean, the shop air is being sitting at room temperature roughly, but since it is undergoing an expansion process, it is cooling down in that process. And you could calculate that, but it depends then again on how long is the compressor running, what is the intake temperature, all that kind of stuff. So let's say we're around 5 to 10 degrees. Let's put that probe beneath our heated up hot end and see what the temperatures are there. So I'll be pointing that right in the connection point of all these valves that blow the air across the extruded filament stream. I'm just going to crank up the full cycle of cooling, up to from 0 to 2 bars roughly. So basically when I'm right in the middle of that point, and I can feel it with when I move it in my hand, it goes up to 26, 27 degrees. So what happens is that the cooling stream is actually drawing a lot of heat from the nozzle tip itself. And yeah, that is consequently giving us higher ambient temperatures from our cooling media. So let's say this is 25 degrees to begin with as a reference starting point. Now I'm gonna set up the first test with the dry ice and see how low of a temperature we can reach here effectively at the nozzle. Alright, so I got the chiller in position. All of this is either copper or pressed steel fittings, and for the last like 20 centimeters we're using a Teflon tube, 4mm inner diameter, which is wrapped in some insulating material and then wrapped up with some Kapton tape. I'm gonna do the first filling with dry ice and then I'm gonna run the same tests and see how low of a cooling temperature we can reach and what the hot end is saying to being cooled as well. So this was one of the shortest first tests I ever did, because not a single time in my whole preparing I was thinking about that the system actually moves and the connection can't be somewhat straight. I don't know, let me check what I do here. But we're gonna do a first few measurements. Let me run some air through here. So the lowest value I could see on the screen was negative 50-ish, somewhere in that neighborhood. But then again, we have to cover some more distance, and yeah, originally this was my plan A. And let's do it again with this added length of tubing. So let's say in this tube arrangement it doesn't lose too much, maybe a few degrees. But to have this being able to move up in Z, I think I'm gonna have to do a loop, because the problem is I'm quite aware that this printed PLA piece will become kind of brittle when it is being cooled, just like the rest of it, because essentially all the air is going through this part. If I put too much stress on it, because it also has to pull that kind of stiff tubing, it is very likely to break, and I don't have a replacement here. So let's say we use this length of a swirl. This is maybe 50 centimeters in added length. Let's see how much temperature this picks up again. Once this thing found its equilibrium in terms of temperature, I think we're not gonna lose too much, but have a look at this. Tubing is usually very flexible. This is rather stiff. I can't really bend it here. I can do once it warms up, but let me take the swirl right to our cooling nozzle situation and see if I can move the whole range with this apparatus. So this is the loop, and we're currently at the highest position. Let's go to the print bed. So as you can see right now, this is taking the movement pretty good. Let me cool this down and rerun it to see what's happening. So as you've seen on the temperature probe, it was somewhere negative 16 or something. Let me just run it all the way back to the to the bed and see what happens. I don't really have an option in terms of speed. We're just gonna go full. Okay. Before we were at like 25 degrees plus. Now we're at negative 16. So let's see what 40 degrees centigrade of difference actually does to cooling. What I can say is it has been pretty hard on the duty cycle of my, like the tip heater. I installed this guy here to give way more voltage to the lower heaters. With this running at full blast, it was just able to keep up its temperature. Let's see how that is in normal printing moves. Well, I'm just gonna start the first print, the first benchy, with 1 bar of cooling pressure. Usually we're right about 2 bars. So let's try to print something with this kind of setup and see what the results are like. You can see the filament is really brittle down there. I mean, you can't really see. This test is designed, it starts with 100 millimeters a second of printing speed and does like a solid foundation to adhere good to the printing plate. The first few layers will do fine without cooling, and we're going to crank it up after that. But this is looking no good. Let me stop that. So as you can see, this is absolutely brittle here, and I've never seen something like this before. Maybe I should have just left cooling as is for the first couple of layers, but I wanted to like pre-chill everything here, but this isn't necessary. So I'm gonna reapply this masking tape before I get all these little debris things in the like air bearing situation. I've never seen filament being so brittle. So let's rerun that without any cooling in the first whatever millimeters. Alright, that is looking good. There are 3 bottom layers. I will run them without anything, and I think I'm gonna ramp in cooling at about 300 millimeters per second, which is at 10 millimeters of height, somewhere in that range. If you're wondering, we are running 50 square corner velocity and 500 km of accelerations. If I don't have these values so up there, it won't actually reach 1500 millimeters a second right at the top. Soon it will hit the second stage of 200 millimeters per second. Right there. And now the whole process will speed up significantly. This is 300, I'm slowly gonna ramp in the cooling. So I decided not to run it all the way to the end before messing up something. As you can see, this is properly uncooled. Interestingly, as soon as I started to somewhat bring in the cooling air, it was immediately not sticking. This is kind of interesting. Let me think about that for a second. Why does it have its shape like that? Clearly the diameter in here isn't the same as here, but this is a cylinder after all. And I think this was at a point where I didn't have the cooling on. I have to check a few things, what's going on here. Maybe we'll do a reprint. So I reran the test just with the original cooling situation, and while this isn't a 100% replicate of the things I did before, it shows the same pattern. So it's again good up to like 1,000 millimeters a second, somewhere in that neighborhood. I have no idea why this turned out like this. I've hooked up the dry ice cooled air again. Let's rerun that test. Alright, this is 200 millimeters. When it goes to 300, I'm gonna slowly ramp in cooling again. So let's have a look together at what we found here, because I think this is quite interesting. So both of these are done beforehand. This is my check to see if everything is working, and this is the one I did before. As you can see, it all starts to go downhill at the 900 to 1000 millimeters per second mark. And why this has turned out differently than this one? Well, there are a few options. I think most of it will have to do with placement of these needles. Even if they're just slightly off than before, it makes a huge difference. And actually, this is way worse than it might actually look. think about it, if just one layer doesn't stick, next one has a lot harder chance. So eventually there has been some kind of a failure in here, and then the rest was just not being able to keep up. As you can see here in this part, it doesn't look good, but it's way better than, like, say, on this side. So let's take this one as our reference. Now comes this guy into play, which we just printed with the dry ice cooling. So first off, this is exactly the 200 to 300 millimeter thing where I turned on the cooling before it was without. But if you compare these two, there's actually a difference to be acknowledged. This one has maintained its value at least 200 millimeters a second higher than the old one. And here, have a look at this again. This is a prime example of an elephant foot. So I guess there are at least two things to see that happen here. So first of all, I wasn't quite sure about why, and this has been like for all three prints we've done the same. The second I turn on the cooling air, it starts to go downhill quite fast. But this time I kept going and increased it in very slight increments. And somehow it catched again and yeah, did this print. First I thought that maybe there is some kind of a humidity or something that is building up inside of those cooling tubes, and once I start to actually circle air through it, it might blow some stuff on here that is not doing any good, adhering, etc. But yeah, the thermal shock that this part has experienced is quite obvious. So let's say this has been at, I don't know, 60 degrees centigrade or something, was able to stick the next layers up there, so it is somewhere in the glass transition temperature range. But then I hit it, even though with very low amounts of it, but this is not moving very fast either. So I was hitting it with low amounts of cool air, and it caused a very sudden shrinkage of all of that. Once it catched up again, and this is a part that has been bugging me a bit, the diameter actually is the same again. So why is it thermal shocking here, but once it starts going with a decent print, it does follow along? I have to think about that for a second. Either way, I think we can derive a lot from these three prints. This has some promising results, I guess. Even though for just the 40-degree temperature difference, we could probably up our printing speed by 20% just by doing that. That is quite interesting. So the question is, how do we ramp in cooling air efficiently without messing up the part? Let me think about that for a second. At least I started some kind of a documentation on all these parts, and I think we're going to rerun this, and I try to ramp the cooling in a bit earlier, but a lot softer, I guess. Let me see if I can do that. And I think we were at the end at around 1.5 bars. I said I'm going to do 1, but yeah, it's too much to do at a given time, especially when filming. So I tried to set this at 1 bar's top and run this again. Maybe we can get a complete part. Let us see. So we just finished the bottom layers, and I'm gonna do my very best to feed in the cooling air as slowly as possible. 200 meter again at the top. Nope. So it was looking kind of promising. I did have some flow in here, and I was very careful to slowly rank it in. But yeah, somewhat happened here. So maybe this defeats the whole purpose of increasing the temperature delta. But this time I cranked up the extruding temperature from 200 to 215 degrees just to see if the incoming stream of air is enough to not cause layer adhesion between those lines. So let's see where we end up there. We have a temperature delta increase by 40 degrees by cooling media, and now we're up in that with more extruder temperature. So let's see what 25 degrees difference looks like. So number 4 and number 5 with 215 degrees. This was actually looking pretty damn solid, and then there was a really sharp transition where it all went to hell. This was set at exactly 1 bar, and as you can see, we made it again up to like 1000, maybe 1100 millimeters a second. Maybe we were on the right track. Let me do 230 degrees, just ballpark, throw numbers at it. Let me see what that does. So 215 degrees, 230, this was actually not moving in the right direction. There was the sudden stop again at the same height, but there were some other blemishes along the way. I'm gonna dial it back to 215 and go with half a bar of pressure on the cooling. Let's see how that will affect it. So both of these are comparable, both at 215 degrees, 1 bar, half a bar of cooling pressure. It somewhat exceeded the top, just a slight bit, but it didn't look too good here. So to conclude this, let's run it at 215 degrees and at a controlled 1.5 bar and see if we get rid of those blemishes, but also how far we make it to the top. So full circle experience. This brings us back to print number 4 we did. As you can see, these are pretty similar. Both were okay to, let's say, 1100, 1200 millimeters a second. I don't really have an idea why we got all these little knobs and crannies here, since they're all or mostly on one side of it. I guess again the needle situation is not symmetrically aligned on the machine. If you just have a look at this here, this is maybe even good to 13 to 1400. It's almost midnight. I'm gonna try to 3D print a benchy. I have no real idea how to ramp in the cooling. The point where I slowly ramp it in is always the spot where it gets wild, and I have to do it slowly, and this part actually allows me to do it. But this isn't the case on the benchy. I need pretty much cooling from third layer on, and then I need it full blast. So I think what I'm actually going to do is run that benchy at like 10% speed, let the whole system equalize and get the cooling pressure up to, let's say, somewhere between 1 and 1.5 bars. And then once I've established an equilibrium, I'm gonna go with 100% printing speed. So let's do that. So you can see just as much as I do. This is babying the first layers. I'm now gonna start slowly ramp in the cooling. By the way, I turned the temperature down to 200 for comparability's sake, because the first was actually done at 200 as well. So let's do 200 and then 215, which seemed to be our sweet spot from the last findings. So first layer done. Half a bar. One bar seems to be okay. I'm gonna go with full speed. Yeah, and we can stop here. I mean, I guess the procedure did work. I mean, I had 1 bar of cooling and it was working up this point fine. So I'm gonna go ahead with 215 degrees right away and see if we can get this to finish. So again, we're at 1 bar cooling pressure. This time I'm gonna slowly ramp in the speed. Ooh, hell yeah. Ooh, so I wasn't really expecting that to happen. This is our reference. The only difference between those is this is 200, this is 215 degrees. You can ignore basically everything below this point here because this wasn't at the reference speed. But apart from that, I'm pretty shocked at how good this is looking. I mean, of course, we're still far away from a quality whatever Banshee, but let's have a look at a few details. So starting out on top, you can see this is getting from reflective to a bit more matte. This is where I was on reference speed. And while this overhang has been sagging pretty much, this is not. And then the biggest difference, have a look at those overhangs here. So having, let's say, 1 bar less of pressure that is actually pulling those strings down does help a lot. I mean, this light and this filament doesn't, it gives you full credit over what's happening here. But let's focus on the upsides. Have a look at how crisper these overhangs turned out in comparison. You can see that on all sides, that there is way less material being blown away. We're essentially using half, less than half of the cooling media from this previous test. Have a look here, right at that line I gave it the reference speed. This one did really fine, while the original one did had problems with the overhangs here. There's a lot less of these small little boogers here at those pillars. Top surfaces look pretty identical, I guess, but overall I think this is the better print. And this is a very promising first result. I know you guys want to see me pushing this machine further and further and reprint another Banshee, etc. But I think it's past midnight. I'm gonna leave it as is because the machine is running really consistent right now. I had like 10 prints back to back that worked out. And I think we're gonna move on to our next approach and then see what we can derive from all of these findings. I'm quite pumped about this one. So it's the next morning and let's do some quick morning math to figure out what we saw yesterday with real-world application results here. First off, let's have a look at the temperature difference in the airstream. So our initial temperature difference was 175 Kelvin, and after we cooled it down with the dry ice, it's 215 Kelvin. Since this is a proportional context, and since the heat transfer between two parts, essentially the PLA we're trying to cool as well as the cooling media, is a proportional context, we can divide those two and see that we gain around 23% in terms of heat transfer capabilities of our cooling stream. There is another thing that's happening when we cool down the air, and this is the density. So let's say at 25 degrees of cooling temperature, we're around 1.18 kilograms per cubic meters of air. And after we cooled it down, we're around 1.37 kilograms per cubic meter. And then again, since the molecules are now closer together, also for a given amount of volume, the heat capacity goes up. And this is another 16% of gain. And if you combine both of these, we got a total of 42% cooling improvement. 42 seems to be a good answer to the thing. I know, this is really leaving out a lot of stuff and it's oversimplifying the thing, but just to get a ballpark picture here. Because what I actually don't know is how we affect the actual flow rate of the cooling media. So we may have higher density, but that doesn't necessarily mean that the same amount of air is exiting our cooling duct. And since this has been on the machine, the dry ice sublimated, I guess is the English word for that. So it went straight from the solid phase to the gas phase. So while this is at the machine, I'm gonna pour in the liquid nitrogen and first do a rough test where we end up. Maybe I will also just fill it halfway to get an additional data point. Last time we had a temperature difference of -40 degree Kelvin. So let's aim for something in the middle, like let's say -80 or 100 or something. The new bottleneck will be the tip heater here. So this is just filled like somewhere to here. It's like, don't know if you can hear all those crackling of the styrofoam, etc. Let me see if I can get that all into one shot. So as you can see, even this small amount pretty much goes down -105. Maybe even more if I would be able to center it here a lot better. I also like the looks of it. So I guess let me just hook this on and see how much of pressure I can apply to the cooling duct while the PID control can hold its temperature, and then get everything set up and running for printing. Okay, that is looking promising to say the least. I was like fooling around a bit. Everything has gone into like with a solid layer of ice on top. With the temperature probe I could sense somewhere in the range of -110 at the outlet here. So these are pretty insane numbers. It will be kind of hard to maintain that at a constant temperature at the outlet because I have to refill this quite often, and if I pour in some new, the temperature will drop very fast, and then yeah, it only takes a few minutes before most of it is gone. Just had very small amounts actually in here. But these seems to be sufficient, and also the tip heater seems to be holding up quite good because I think the placement of those air outlets is kind of favoring it right now. It sits kind of low. So I centered everything up. I will refill this with another liter, and then we're gonna see how I'm gonna ramp this in slowly. We're gonna start with the temperature cooling cylinder again and see how far we can make it, if we're gonna make it at all. Let's see. So this whole system has to settle in and yeah, get all the lines cooled down, and then I guess maybe -80 at the below the nozzle is possible. very slowly ramping in. Okay, stopping it here. Got the probe sitting in the infill somewhere. Since plastic isn't the best of a heat transfer, it took a second to settle in. This is like 1.5 minutes after the print. But it's still, let's call it cool. So when I removed it from the build plate, it broke down here at the most solid layer. And all of that junk that is being left here on the print bed is actually very, very brittle. I mean, the print bed itself isn't too cold, at least not now. So this is it. Again, we made it somewhere. The 1100 millimeter per second part went through, and it is looking very, very good. We were at 215 and half a bar, so that corresponds to print number 7 we did with the dry ice cooling. And I still have no real idea what happened here. Those boogers here are a fluke. I have no real idea about that. But what is a fact is that pretty much all of them are cancelling at the same height. And I begin to wonder if that has something to do with the code I'm running. So maybe I'll try again to get the temperature up 15 degrees. This pattern I seem to recognize from the extrusion temperature being too cold. Not necessarily the values in Clipper for the PID control of the temperature are okay. There is maybe a drop of 2 to 3 degrees or something, but maybe this is just too cold and doesn't stick to the previous layer. So I will rerun the test and try to do a slow motion shot of that upper part and see if we can see something regarding why this isn't sticking here. Let me do that. Alright, so nothing in the code looked suspicious. I'm gonna run it again, this time at 230. I'm gonna ramp in cooling just like the last time it did seem to work. But as you can see here, this is quite interesting. There seems to be some kind of a liquid in the way of the air bearing. So this may be alright for a few prints, but I have to see how we do with that. This time we made it to the end. Let me get that down and inspect it under some good lighting. So this one finished. I still don't know about the booger situation, what is causing that in the first place. It seems to be on or off during prints. What's interesting, in a few spots, if you get rid of those boogers, it kind of looks pretty good all the way to the top, maybe to, let's say, 1400 millimeters per second. I'm gonna keep rising temperature. Again, put on another 15 degrees. So big of a temperature delta, we can justify putting a bit more energy in the filament. Maybe this still is due to low extrusion temperature. Let us see. I refilled another liter of nitrogen, and this is running at 245 degrees C. Nope. Okay, it was looking rather good up to this point, and then it didn't. So what I do notice is that these kind of artifacts are most of the time happening at a transition to a different print speed. The material is suddenly coming out of the nozzle with a different temperature because it is being accelerated a lot faster, but I get that maybe from 100 to 200 millimeters a second there is a big difference, but from 1000 to 1100 that's just 10%. I don't think this really adds up. But then again, if you have a look at benchy printing speeds, you're maybe going outer wall 700 millimeters a second and then infill at 1500. So yeah, I guess those kind of parameters are there throughout all of 3D printing. So I guess this can't really be a problem, but maybe this is a thing to have a look in Danger Clipper to have a predictive move on the hot end temperature. Maybe this is something we have to deal with. I'm gonna rerun this because the bottom was actually looking quite good, and I tried to go even lower with the pressure. I have a 10 bar pressure regulator here on the setup. I'm gonna switch this out to a system that is a bit more fine controllable and see if I can dial in, let's say, 0.25 bars. Also, nope. Don't really have an idea how to explain what's going on here. These are the facts. It most likely happens at a transition to a different feed rate. You could potentially go ahead and manipulate the G-code in a way that it does it incrementally, just by 1% each layer or something, so there isn't that big of a feed rate shock, I guess. But in my particular case, this isn't possible. I do it on the slicer side and have like 15 different height modifiers added on top of each other. So this is out of the question to do it by hand. Let's just freaking print a benchy. I'm gonna go ahead, dial into 15, just like we did yesterday with the dry ice. do the same exact procedure in terms of babysitting the very first layers, then cranking up cooling to a certain point I want to have, let's say 0.5 bars, and then slowly ramp in the speed so we can like at least compare the top halves or top 2/3 against each other. Let's see what happens. This is how far we made it. So my theory is there is, in this case, just not enough cooling. And the reason for that is that this system is pretty iced up. So if you have a look here at the pressure regulator, you see pressure is rising and rising and rising, but the airflow is not increasing as well. So I guess there will be a lot of humidity buildup that is being like run in those cooling lines. I mean, the air is transporting the humidity. This is most likely having built up in all these fittings or maybe in the copper tube as well. I could do two things right now. First, I'm gonna let everything cool off, place it outside in the sun, and maybe repeat the test in a few hours. Or I'm gonna pour in all I got, fill it all the way to the top, and try to cool with a very, very low stream of air that is being super cooled, and maybe reach like negative 150, 170, 180 or something here at the nozzle. But I think, and that would be a bummer, if I pour in everything and it clogs up completely, then I have nothing left to conduct further tests. So I think I'm gonna go with option number 2. I think it was option number 1, but anyways, I'm gonna place it outside, move on to the next test, and maybe revisit that setup. You know, there are several ways you can actually support me and this particular project. So on one hand, there is a link to my Discord somewhere down there where there's an active discussion about all the topics here, and you get a lot of more insights than even in this freaking long videos. And if you want to support me with a few bucks, you can now do that over there on Patreon, just like I introduced it in the last video. So these are the OG7. Thank you so much for supporting me here on this project. Thank you. Moving on with our testing, let's have a look at the next approach I've set up on the machine. And yeah, just before you say it, it's not certainly decreasing the complexity of the whole system. So let me give you a walkthrough. So this is a Eurobox stacking system type of thing, which I 3D printed some adapters to the back, which accepts shop air. And then having a look inside, there's one of those ultrasonic fog things. This is a 10 head, I guess 600 watt unit. No, it's 280 watts unit, and it's sitting here in just plain water. And when I flip the switch, this thing will start to produce water vapor, really fine water vapor to be precise. Now, this is our current cooling situation, just as you have seen in the last couple of episodes. And let me put on a bit of air through it. So what is happening, because these are angled downwards, it is actually going to create a vacuum zone up here, right in the middle of that ring, I would say. And now we're going to use this contraption and blow a fine stream of air through it and through this hose, and at the end of it there is a very fine fog exiting, and through this vacuum zone it will be sucked in right into that cooling stream. So let me And now you can see why I built this like enclosure thing in the first place. I have to shield this whole hot end by not being blown cold by the water vapor. And as you can see down here on the tray, there is a very fine layer of humidity building up. Let me increase pressure a bit on the cooling side. So in a perfect world we wouldn't be having those bigger droplets, we would have just the fine mist over there. So let us just have a peek inside this technology. Water is actually a very, very good heat conductor and also has a very high heat capacity. The best case scenario would be to have a very fine fog being like deposited on the extruded material, and if the amount is just right, then all the water will be evaporated at the end of a print through the extruded material. And if you change any kind of material in terms of their state from, in this case, liquid to gas, it's going to take a lot of energy or draw a lot of energy out of the system. That's at least a theory. In practical applications, this means I have to control a lot more dials and knobs, and also there are so many parameters that play along with each other. So now we got pressure on the cooling duct, now we got pressure on how much vapor we're going to blow into that stream. So yeah, we have to guess a baseline. I guess for the very first time the whole theory behind it is to have less air pressure on the cooling duct, because this will blow our extruded material downwards and mess everything up. So we're going to start with half a bar, and then I'm just going to very, very slowly get the vapor in to not over cool everything or have it like blown away with all that liquid, because what is going to happen for sure, air bearings don't like moisture, and this will definitely become a problem. And if we're going to stick with some kind of this approach, then I'm going to have to engineer something that keeps the moisture away from the air bearing. Air bearings in general tend to use the most dry air you can get. That's why whenever I'm running like these machines or something, I do have air triple filtered and demoisturized. And now we're going ahead and fully blowing this stuff onto here. So I have no idea how long that will take, so that's why I was planning to do that the very last. We'll see if that works and we can get like the full run with liquid nitrogen again. But let me start. I think I have everything set up. Let me just start with the cooling benchmark tower and see if we can finish a print. Alright, first layer seems to be okay-ish. After like 100 millimeters per second, I'm gonna introduce the cooling duct and then switch on the vapor very, very slowly after that. Half a bar. Okay, and we got vapor on the lowest setting possible. So filming isn't easy on that machine, well, like running it by myself anyways, but this has even kicked up a notch. Let's have a look at what we got here. So as you can see right here, around that brim, there's actually moisture built up. And the rest of the build plate is a bit damp, but other than that, it seems like the amount doesn't really build up inside the air bearing. Let me get that off the build plate. Oddly enough, at least this print finished, and we were at the very lowest settings. So I think there are a few very promising things in here. First off, the air bearing didn't crash at the very start. Let's have a look around. I think this is somewhere in the range to, up to 700 millimeters a second it looked perfectly fine, and then you could argue that to 900 millimeters a second it also looking okay-ish. On top, the cooling amount was just not enough. That is easy to tell. Just in case if you're wondering how it is possible to have that sticking at these high speeds, even with very high first layer prints on a cold bed. This is the stuff I'm using right now. I've had problems with other types of glue sticks, but this one is working really, really good. And if I don't mess up the masking tape beneath it, this is doing, right now this has done 10 prints with a single application of this, and all the prints stuck to the end. In terms of layer adhesion, I have no real scientific method of testing that. I guess the top here, yeah, this will break, but that was to be as expected. But down here, I'm feeling a crack here, but I think everything down here has to be considered somewhat solid, so not brittle as fuck. To say it again, our main goal is to keep the main pressure down, so we're going to stick with half a bar on the cooling duct, but increase the amount of vapor infusion this time. So these are the two in comparison, the one before and the one you just saw. They made it pretty much to the same height. It's again somewhere, it completed the 900 millimeters per second step. And then a very sudden transition to not working at all. I was giving it quite much of vapor at that time. What I think is quite interesting, the evaporation has continued, but the lower part was pretty much soaked, but the top part didn't have any moisture at all. So I have no real idea if the vapor is being deposited at where we want to have it or not just being blown in some kind of direction. So for the next one, I'm gonna do a bit more on the cooling duct side to see which one of those influences cooling the most. So 1 bar on duct side and increasingly higher vapor infusion. This is the last print. This one is actually from just plain Shop Air, our reference model. Up to this point, they basically behave more or less the same. So the question I got in mind is, where is all the water vapor going? So I'm gonna rerun this and set up the slow motion camera and see what we can derive from that. I took a very bad one without any lighting, etc. And what I could see is that there was vapor in the air all around, but it seemed to have like nothing to do with the print itself. Let us see if the slow motion footage will reveal any new insights. So this is the print you just saw in that slow motion footage, and I'm very glad I did it, because even though I just had a quick peek at the camera display, this does give us some great insights, I guess. So I did mark the position that was nearest to the vapor outlet. And if you have a look here, I mean, all of that has not worked so great. We made it somewhere to, I don't know, 900 or something. I mean, it's still very, very fast, but not where we want to end up. But have a look at, like, this is the best spot here. And also that vapor outlet was offset quite a bit to that region. So I would say it did pass at least the 1000, but more so the 1100 millimeters a second mark. Slow motion footage, you can clearly see that if the nozzle is somewhere here, then there is pretty much no vapor flow going down that thing, and we're only running 1 bars of cooling pressure, which is then the effective way of cooling. But when the nozzle is right up here, then you can clearly see that all of this vapor is being deposited right at the edges of our print, and that is exactly where we want to have them. So maybe the first conclusion does have to be that we need to have it in circular order and get all of that vapor surrounding the print, so you don't just get like a chocolate side here. Let's print a benchy. So if the task would have been to make a horrible mess, aced it. This is our reference benchy. This is the one you saw me printing the last. It detached right around here. I have to reapply that masking tape. The water isn't doing that any good. It's soaking wet. But other than that, if you have, I mean, this is 2 bars of cooling pressure. This is 1 bar with vapor. And if you have a look at, let's say, just the bottom part, you almost can't tell them apart. It's pretty much the same. This is the back side. This is the front side, where, I mean, it is located like this on the build plate. Therefore, the water vapor hits it right there. This part is actually looking worse. And also right on top of here, you can see that nothing of that crispness that this 3-minute 20 print has is being translated into here. I just realized that this thing is pumping like constantly almost 300 watts of essentially heating power into that water. It is lukewarm. I can feel like 30 to 40 degrees right here on the outside. So let me top that off with fresh water, and just out of curiosity, let's put some dry ice in it. See if we get real cold vapor, if that is doing any difference. Now would you have a look at that? This is purely self-propelled. I have no air hooked up to this. So let's see if we run it just CO2 vapor only, or if we're gonna hook up the vaporizer again and use just cold water. So this is going to be a very tough decision what to make out of these findings and tests here. Again, print number 1, print number 19. We did lose the bottom like 3 layers or something. Yeah, but have a look at what came out of here. It's a struggle between maxing out the cooling and not blowing the air cold. It was maybe 2 or 3 degrees before the PID control would have gotten into error mode. So it is a very fine line to get this going. And I think somewhere at this point here, I was giving it reference speed. And if you just have a look at the upper half, I mean, basically this thing, this may be one of the best looking we've ever printed here. I mean, look at this overhang. This is the one compressed air. And this is the one CO2 cooled, which was like the best looking before. Everything here is super crisp. Not the other side. Again, this is the side where the vapor is actually infused in the stream. So you can see what kind of a difference it makes having water vapor in it. This time cold water vapor. I guess it's somewhere in like 5 degree range. The previous one, this one here, was with approximately 40 or something. It was way more when I dumped it in the sink. So again, this looks kind of promising. It is a total mess on the machine, but before there was the need to, you didn't have printers that could print PEK or something. And then some engineer took the chance and built something in an environment where you can heat up a chamber up to 200 degrees. So it wouldn't be a problem to have all that mass contained in a machine and not destroy air bearings and such. I don't want to disappoint you, but I was looped up and ready to go for another run with everything I got in terms of liquid nitrogen, but as it turns out, the container was already empty. I didn't notice that before. I was really planning to do another test, and I would have liked to at least try to print a bench sheet to have that in like my benchmark catalog, but it is what it is. So Let's straight jump to my computer and have a look at all the things we did learn today. What did we learn in general about engineering? So all of the things I do here follow the same principle. We want to do fast iterations, we want to fail early, and we want to fail cheap, as well as we want to build the most basic prototype that proves a point. And if you expect perfect results in the first test, you're very likely to get disappointed. I'm really happy with how this has turned out here, and yeah, we're gonna follow along with everything we can conclude here from now. The thing I tried to get in terms of documentation, get a lot of data points and then see where like ballpark areas where it was like working the best and where it did not work at all, and then get in those peaks and see in what kind of direction we can move from there on. So also I like to question myself about known facts you got on your mindset every once in a while, and that is happening right now. So is cooling really the issue here? I was kind of certain here, but I think, and we're coming down there at the end of this document, I think there are few things we have to reconsider, and I hope we're gonna do another printing round in this video. What kind of is bugging me is the sudden transition to not extruding properly. We have to investigate what that is all about. And maybe for the future, we need more sensors on our system. Whatever those are, but yeah. Everything here regarding discussion on learned topics, lesson learned, etc. down in the comments, please. All right, so in absolute general terms, the complexity of this system goes up, no matter what of these options we're using there. Next big thing is plastics, and who would have thought that? Don't like to be overcooled, they become brittle. And it is kind of I don't really know how to distinguish that in terms of the first layers. If I overcool those will get really brittle. Everything else in terms of mid-print did somehow work, and layer adhesion was good, and the prints were not too brittle after they like accumulated to room temperature. And again, one of the first main things here is I think it is not desirable to cool down our prints way below the glass transition temperature. All that matters is how far or how fast can we like get it down there. The higher temperature delta does help us with that, but then again we might really overcool the thing. So maybe this is one of the things that are pointing towards something like the water vapor cooling, because this is not going negative temperatures or something, it just helps it to drop temperatures really fast to ambient. For everything we have put in terms of approaches, ramping cooling in was a huge problem, because yeah, you suddenly like start to change all of the PID controls, and extruded material comes out at a different temperature, and the already extruded material suddenly shrinks, etc. So this will be kind of a problem in the future. And then again, cooling media is expensive. So I've listed it here: the fan, followed by shop air, water vapor, dry ice, liquid nitrogen. We're coming to costs in a second. So let's cover everything we had so far on any machines here. So a fan setup is really proven with clear limitations in terms of flow and performance. We can control it very good with just a PWM signal. It's dirt cheap in terms of running it, but what we kind of need is a like open duct design that offers very low air restrictions, so we can get somewhat airflow, because fan systems don't like to build up pressure. In terms of heating or cooling capabilities, we're basically blowing around air temperatures in terms of a fan that is sitting somewhere next to hot, and it will be even have higher than ambient temperature. And then of course we're going to pick up the same with everything else, the heat that is being distributed by the hot end or nozzle in that case. So I estimated that at room temperature we're going to pick up 25 degrees just in like ballpark in all the other tests, so we're coming down to a effective cooling temperature of 45 degrees C. The shop air setup. is more expensive than a fan solution, but less than anything else. We get a little bit of chilling effect on the air because we're using the expansion, and we measured that it is around 25 degrees C after the nozzle, so effective cooling temp. Also, I never had really problems with ramping that in. It was not throwing off any PID controls or something. It just was a no-brainer in terms of how much did I throw at it. And then, yeah, some of our main issues, the high airflow we got, and it is pointing downwards, that this has like several reasons why it is like it is. Mostly it's the mechanical construction. For like first layers, etc., I can't really have it like pointing upwards because there's a glass plate or a build plate in any other printer's case. This is a pro and con. We can use different duct designs, but also we have to use other duct designs. And yeah, we got a lot of data points using shop air to dry ice. So at least here in my region, I paid 20 euros for 10 kilograms of that stuff, and it did last quite some time, and it was very safe to handle. No safety hazards there. I had a fan running to not get too much CO2 here in the air, but this is let's call it a well-ventilated room here. Depending on how much I fill it and how long the whole system had to find its equilibrium, we hit around temperatures of minus 35 C at the nozzle. So quite a delta we reached there. And this, as shown before, theoretically improves cooling by over 40%. Since we have more heating capabilities, we can reduce the airflow and therefore have better overhangs, which we could see also in the prints. While we had huge problems with humidity buildup with the liquid nitrogen, it didn't seem to be a problem with just the dry ice. What we did notice is that transition zones between working and not working were getting a lot sharper. While with fan and shop air, you could see a change over some time. Dry ice, it started being like from one layer to another, it suddenly wouldn't work. Whatever reason, we're gonna find out about that. Also with dry ice, we started to run into problems with our PID control on the nozzle setup heater. I think I have to put on a lot more power on that. So both of these ceramic heaters are rated for 84 watts, but I can't really see those digits somewhere on the power meter. It's more likely to be 50 watts combined with the two of those. And even when I gave them a lot more voltage, yeah, they clearly weren't catching up with the demand of heating power. So I think I have to address that for future to have that cooling proof. So no matter what cooling I put on there. Also, I have to move the sensor a bit downwards to get a more reliable PID control on what's actually happening on the nozzle and not like 5 millimeters up the line. Liquid nitrogen. I paid around 50 bucks for 20 liters, and right now this is quite an inefficient setup because there's lacking insulation, etc. But I was really surprised on how fast I've gone through this stack of energy basically. And while that wasn't really a safety hazard or something, you have to take precautions. You shouldn't get this on your clothes. I mean, just think about, I have a container with a tube where shop air, compressed air is going through. If one of those fitting blows at negative 200 degrees C, I'm gonna have liquid nitrogen burst all over the machine and probably myself, and that will cause burnings on the skins, etc. So I'm quite aware about the safety risks involved. Sophisticated machinery will have that all outside of the machine and then have insulated tubing going in, but we're not there. And who knows if we're going to stick to this metric here. But what was really interesting is that we could reach temperatures of minus 130 degrees C at the nozzle, and I was, as I said, by the minute I poured it in, it was already like all gone. It was just the heat then being captured in the copper tube. If I really would have like filled this up all the way to the top, found equilibrium, we would have reached even lower temperatures than what we had here in the test. This isn't true. This should be more like 300% of theoretical improvement. But yeah, there are so many parameters with that test going on. I have no idea where we're there. So let's discuss that in the comments, please. There were some cases where we could think that the overhang situation was better because, yeah, we have more heating or cooling capabilities but less airflow, so the downward force is not there. But then we had problems with humidity building up. You saw that was really clogged the system, and when I had it outside in the sun and put it back here, really nasty goo came out of that, maybe 50 milliliters of stuff that had like accumulated at the bottom and fittings. And yeah, ramping in cooling became even more of a challenge than anything of the previous attempts. I had everything concerning any valves or something that could regulate that is really expensive stuff. So I don't want to get into that before we find like this is the approach we're going to follow for long-term use. I know there were a few options, so you may be surprised that I use air and then cool it down to get temperature delta up. We could also have used the gas phase of the nitrogen instead of air. And we could also have used the fluid phase and directly spraying that on. But I found that in both cases, I mean, the air setup is here and I can use it and it is manageable, but you need really sophisticated equipment in order to do all the other stuff. And I just had a rental container, which I wasn't able to like weld a bung on or something, so I didn't want to mess with that. But also I typed a lot of emails to companies that build cryogenic cooling applications. But guess what? I never got an answer on that. If I want to use their multi-six-figure equipment on a 3D printer. But yeah, that's what it is. If we want to go that route, we have to build some serious equipment, probably by ourselves. Coming to the last approach, water vapor. It is not too expensive to run. Routing it becomes kind of a bottleneck. If I tried in previous tests, I tried to put it through a like smaller diameter hose, and then yeah, like you got so much back pressure that all the vapor like condensates on the tubing walls, etc. So I found this, I think 60 millimeter diameter tubing was what works, and I could transport the fog to a state where it is usable. The fog generator itself needs to be kind of that big as is because you need a certain height, so it develops. If I make that smaller, and I tested that, you won't get any fog out of these ultrasonic devices. And then I don't have really much other space on the machine where I can put it like on the Z-axis or something. So these like 40 to 50 centimeters of tubing, I basically need that. Certainly my air duct is drawing a vacuum on top. But then again, it is depending on where in a print it is. I just tested it statically beforehand, and then it was working quite well, but depending on if you have a print below the duct surface, then there is suddenly no vacuum and all the vapor like escapes to the top. So we have to have at least like a circular thing that distributes all the vapor to the print, and most likely where the nozzle is, there is space and vacuum zone, so that might work if we get it in a circular form. Bad adhesion becomes a problem in my case, but I think certainly in every other case, because water that accumulates on the print plate would also heavily cool down any bad surface you have there, no matter what the heater is and how many watts it does have, because you only have like one temperature probe, and it won't recognize if one of those spots is getting like cooled a lot. And of course, the air bearing doesn't like humidity as well, but this is in my very particular case. I guess most of you guys don't face problems like that. But in every setup, it's a total mess in general. You've water basically spraying everywhere. What are the remaining questions for this episode? So most of the time we did encounter like layers starting to look worse, somewhere in the 1000 millimeters per second range, and only In a very few attempts, we reached like 1200 at a certain point, or maybe 1300. Questioning myself, is it due to insufficient cooling? There could be two other options that at least give an answer on this particular cooling benchmark tower. The first one I do have in mind since the very beginning of this project. Is there a limitation to extrusion speeds? We've seen a lot of other people like printing at 1000 millimeters a second, and that does work, but it's on bigger prints. So cooling is out of the equation there. Layer times are, even in this situations, probably a few seconds or something. But is there anything that prevents us from going faster in terms of the material itself doesn't like being accelerated that much? Or is, I don't know, software limiting us in terms of how many steps that are there, or acceleration of steppers or whatnot? And then maybe in our first tests with our reference models, does it look good all the way to the bottom, but then it's just a matter of tipping the whole bed situation? I can't really take it out of equation because it is a very slender and big part in terms of this machine, and then it has been sitting on an air bearing which has a certain degree of flex in it, and then it's sitting on masking tape which is kind of fluffy in itself. So maybe this whole thing is shaking. I saw that yesterday when I was sitting on the computer and watched the footage on a big screen. There is a bit of tipping here, and of course we're running 500k accelerations at 1500 millimeters a second printing speed. Those are insane numbers, but yeah, maybe it is causing the problem to begin with. The benchy situation where we have like these small little pillars, this is a different thing, but in terms of this cooling cylinder. So, long talk. I tried to do two things for this episode. Get back on the printer. We're gonna try to run the same cylinder but in bigger diameter with more infill. So basically we're gonna like quadruple the layer time. So we're gonna take that out of the equation and just see if we can run the 1500 millimeters per second all the way to the top with shop air, to not have it overlaid by a layer time that we cannot cool in this situation. So cooling out, let's just see if 1500 millimeters per second extrusion is possible in general. Maybe if I have it in me, go in the slicer and put all these values at a different place and time and make it wider but less height. So basically we run, instead of 50 millimeters height, we gonna reach 1500 at 25 millimeters. So the tipping effect shouldn't be too pronounced there. Let's see if I can like get the machine running in a fast matter of time. This video will almost be 2 hours, I guess. But I'm curious where our real problems are, and I want to give you guys as much information as possible to have a discussion in the comments with me or in Discord. Alright, so I just started the print. This will take somewhere, I mean, it's estimated over 20 minutes. I made it 60 millimeter in diameter, and it has like 3 parameters and 25% infill or something. So this maxes out our layer time on top, at the very top, to 1.8 seconds. So I guess we can say cooling is out of the equation there. I'm gonna get you updated once we're somewhere in the middle. It's like this each and every time. I just want to do a quick little thing to make like the video be integer, etc. Then one of those lines got dripped out. I basically over tightened it, and yeah, now it's split. I'm gonna give it a last go with some super glue, set it back together. Maybe we'll see more than just that. If not, this might be the end of the video. Second time in this video where I'm like honeypotting you with some kind of a thing we want to do and then it's not happening. I'm sorry for that. This does not work. I gave it a few minutes to properly set and clamped it down with the vise. But it broke as soon as I tightened the screw. So I have to either reprint this, take every of my finding into the MK10 version, or I'm just gonna set it with some epoxy. Maybe I'll do that overnight and decide tomorrow, but by the time I want to have this video also rendering. I think I'm gonna leave it in, because this is kind of a thing in engineering. Stuff happens all the time, especially when you're doing research work, and this is the essence of that. The content I do here is pretty freaking long. There are no 10-minute videos where I summarize everything I've done over the past couple of months or weeks. I'm gonna take you on a uncut and raw tour here. And if you don't want to see that, tell me in the comments, and also, well, just don't watch it. For all the other guys that are into research just as I am, yeah, this is your type of content, I guess. I wanna end this with, I will submit these findings later, but let's just do it in another episode where put me everything I should additionally test or discuss in the comment section or on my Discord or whatever, and I'll try to address it in the upcoming video. Give me your honest feedback on what your interpretation of the results from today are and what I should be investigating in the next. Should we do a couple more, like go with CO2 bottles, try, I don't know, argon, try helium, freaking expensive, I need funds on that. Or if we should take a deeper dive into one of these topics. So I'm really curious what you guys are making out of this situation. Let's have an open discussion, and yeah, I'm gonna end with how I started. I'm Jan, I build stuff so you don't have to. And it was a pleasure to have you guys here on an, I guess, almost 2-hour long video. See you in the next one. Bye.